Okay, com check, com check.
Loud and clear.
Thank you. You should see my screen. Okay, this will look a little bit different from your view of Canvas because it's my view, not your view. But I'm going to add, let's see, where we're going to have everything here. I'm going to keep these modules the same. So we have the first page of the module is always the objectives. The second has the content. The third has a quiz. The fourth has additional resources. The quizzes, as most of you have experienced already, are designed to be stupid simple. It's, you know, have you even looked at this stuff kind of questions. I recommend reviewing this stuff before the lectures. And then the assignments will show up in their own tab. I won't include them as part of the modules. What I've done, I've already put in placeholders for the homeworks. For the projects, you should see all the due dates there. And then you can't see this. That's why it's grayed out. As the instructor, I can see this. Dean is setting up your labs. Labs begin next week. And we're hiring, I think Robert Apelian will be the primary person in the labs and the grader for the homeworks. And Mike Franito will be sometimes in the lab, but he's going to be primarily grading for CS225 for me. I wanted to show you what these look like right now. Right now it says placeholder, even though it's published. So I'll have this actual assignment posted, I believe, tomorrow night. It's not due till September 7th, so you'll have plenty of time to work on it. And it's a really simple homework assignment. It's basically proving that you have downloaded Java, that you can write, compile, and execute a piece of code in Java, and a very simple piece of code. How is the lab? The lab, everything in terms of content for this lab is folded into the CS225, so don't worry about CS225L in your Canvas, and everything is online. So you won't go to, just like this, you won't go to a physical space for lectures, and Dean is going to hold lecture hours at the same time as what was previously scheduled. But everything should be able to be done without attending those if you can't. So don't panic if you can't. The idea behind a lab, typically when we're holding in-person instruction, is that you can go there and he gives a short introductory lecture, and then the rest of it is basically tutorial to get the lab work done. All the due dates for the labs, no matter what day your lab is, everything will be due that Friday. Which is actually nice because during in-person instruction, if we have labs Tuesday, Wednesday, Thursday, and sometimes we have them on Fridays, it does give a slight advantage to the people who have the labs later in the week. So this is a good equalizer. Did that answer the question, Anna Marie? By the way, you guys can unmute yourself and just speak. That's fine. Yeah. Mostly. What else? I've got a message from Dean on that, and again, there's different lab times. I don't care what section you're in. You can attend any of the sessions. Normally, we restrict that in face-to-face because there's, you know, only so many seats in the classroom, but there's no limit to how many people can join the Zoom meetings. So let me check my email real quick. Let's see here. Tuesday 12 to 2, Wednesday 3 to 5, Thursday 2 to 4. And it doesn't matter which of those you attend. They're repeats of the same situation. Dean will set up the Zoom lectures for those.
Do you know if those will be recorded?
I'll recommend to him that he records them and so in post one of them. So for example, I'm doing two. This is my second lecture for this class today. I'm recording both, and I'll pick the one that I think is best and share that one on the course on Canvas. And the way I'm doing that with all of the lectures is posting them to YouTube and then embedding the video in the Canvas. So you can always go to my YouTube page and find them. So let's see, I'll have to work with him about that to see if he can post to YouTube or some other thing, or if he's just going to post directly to this class. But even though he has 3 lectures, he only needs to share one of them. And we'll have to see how that works too. If it's just tutorial, that may not be worth it. He's going to do what he normally would do in the beginning lecture portion. That he's going to do as a recorded video and share with you guys. Okay. More questions? Questions are good. All right. So anyway, I've published these homeworks, even though there's no homeworks in there yet. Most of them are already created. This first one I have to create from scratch, and the other ones we always tweak a little bit from semester to semester. And I'm kind of sharing with them for a reason. This is good software development protocol. You develop software by creating shell programs that don't do anything with methods or functions that are effectively empty. And then you fill them in one at a time or a couple at a time. And what I want to encourage you to learn is to share your unfinished work. So here I am sharing my unfinished work. It's ugly because it's not complete, but that way you get to see it as it's being built, and you get to ask questions about it as it's being built. And if it doesn't meet your needs while I'm building it, I have a chance to fix it. It's historically, I found difficult to get students to finish their work. As humans, we all like to say, oh, I don't want you to see it yet, it's not done. You know, you may have a friend, or maybe you're someone who's very artistic and they're doing some kind of a piece of work, a piece of artwork. Oh, I don't want you to see it until it's done. And I'm going to ask you repeatedly throughout the semester to resist that urge. Show your code off to people before it's done, while it's ugly, while you're still in the design stage. Ask them what they think. Get used to that. That's how things work in the real world in a working environment. Today, in fact, we're trying to get some funding from the NSF, and Professor Babishanu is going to share with me a draft of our proposal, and it's going to be ugly because it's a draft. That's how things work in the real world. And then I'll edit and pass it on to someone else, and as a group we'll edit it and get it completed. So please share your ugly work. It's work in progress. Okay, do we have any more questions about just course logistics before we go into content? Just unmute and speak if you have a question. Okay. I added this module maybe 2 or 3 semesters ago. I used to just start right off with programming in Java per the text, and what I found is students were coming up to me and saying, well, I tried to follow the examples in the text because the text does give a lot of sample programs, and I just didn't understand the language. I didn't understand what I was looking at. So I thought I'd give some introductory discussion about what objects are to begin with, to get you to think in terms of objects, and then also to start talking about, okay, what is it going to look like when you start looking at Java code? What should you expect? so that these things are useful. I'm also taking the author's code. I have a fair amount of arguments with how the author did the code. And technically, I should probably say the author's grad students, they probably did it. I have a fair amount of arguments with just their coding style. So I'm rewriting a bunch of those and we'll post them. And so the way that I post at least some of them, not all of them, is I just give you the bare bones code, and then I have another version called annotated that just throws in a whole bunch of different comments to try to explain within the code what's happening. The idea of commenting your code, I'll talk about in a little bit more, but I'll discourage you from overly commenting your code. You know, comment should be a bare bones minimum. But in this case, the whole point of the comments is just to explain line by line, word by word, this is the reason that word is there, this is the job that it's doing. So next week, you'll start to see that stuff. I'll have it posted prior to then, but next week is when we have that discussion. Also, I have 3 lectures a week. I fully expect we'll go to 2. We'll see how that works out. This is flexible. We're going to do what works. We're not going to stand by on procedure. We're going to do what works for the customers of the course, which is you guys. So if I need to do 3 lectures a week, I will. If I can cut it down to 2 and still meet everybody's needs, then that's efficient. The reason I think I can't get away with less than 2 is one will be about the topic for the week and one will be about, and I think having that project discussion is valuable and requires its own lecture. Okay. As always, start out with the outcomes. Here's what you should know after you go through this module. And for the most part, you know, you can read this, I'm going to ignore it, but I encourage you, after you're done with the module, go back to this page and ask yourself, okay, do I really understand this? Do I have any questions about that? Maybe that's a better question. What do I have about this? If you say, do I understand it? We always, as humans, say, of course I do. And then when you start to work with it, it's, oh, wait a minute, I didn't think about that. So maybe ask yourself, what questions do I have? And then bring them to me, open up, we'll have discussion pages. You can always access me via Canvas. So what's an object? An object. In everyday life, what's an object? That's actually a hard thing to define, right? What is an object? I didn't really give a definition. I gave an example. There's an object in a nice office space reference. Red stapler. Okay, you can say what it is. You can say what category of thing it's in. Oh, it's a stapler. It's a specific type of stapler, but it's a stapler. That's its category or its class. And when we talk about objects, we'll talk about the class, because actually what the software design that you do, every object is in a class file. That's its name. It's a class. You can then describe it. It's red, it's so many inches long, it's so many inches high, it has staples in it or what it doesn't. You can describe its current state. It has location, it has orientation, it has quantity of staples, it's jammed or unjammed, opened or closed, things like that. And then you can change its current state. You can move it around. You can staple something and reduce the staple count by 1. You can try to staple something and jam it. You can fill it up. Change the staples count again. So these are ways by which you can change the state. So that's what an object really is. It's something that you can name and put it into a category. You can describe it, and you can change its state. How does that relate to software? Software objects are exactly the same. They are software objects that have state, that belong to a class, and have mechanisms or methods by which you can change the state. So the word object is not an accident. It's not trivial. It helps you understand what you're doing. The object-oriented paradigm, instead of building one piece of software that runs from the top to the bottom, you build a bunch of objects that do different jobs. Each of those objects belongs to a class or a category. Each of them has state. Each of them have methods by which you can change the state. This current state is described by the attributes. So instead of using the term variables in this class, we almost always use attributes. Attributes describe the object state. And in terms of, instead of saying functions, we say methods. Why? Because it's the method by which you change the attribute, by which you change the state. Some attributes are hard to change. Weight, color, material. I can't change the material of that stapler from metal to ceramic or hay, right? The material stays the same. So some attributes may be constants and some attributes may be changeable. You will find you rarely have constants, rarely, but they do exist. A couple more examples, your car. I don't know, about 10, 15 years ago, all of the books were using motorcycles. Your car has a location right now. Right now, if I asked you about your car, you could describe it. You could describe it in terms of its class. Oh, it's a vehicle, or it has a make and a model. So you could describe its class, which tells us what its design. You could tell us you could describe it in terms of how it's built. You know, it's red, it's got a certain horsepower engine, things like that. But you could also describe its current state. Gas tank is empty. Car is locked or unlocked. Car is running or not running. The engine's running or not running. Hopefully not running because you're here in class. And you have methods to change those states. You can turn the car on. You can turn the car off. You can speed it up, slow it down. You have a method by which you can shift into reverse called the shift mechanism, and a method by which you can go into drive. So you can change the state using methods. Now the methods in a physical object are all the mechanics and gadgetries that make it work. The methods in a software object are what you used to call functions that modify the attribute values. I'm pausing here for questions before we go into the example. I'm curious to see online if we get more questions or less than in a face-to-face session. If you think of questions, just unmute yourself and ask the question. Okay, how many people looked at this before? We use your little reactions to put your hand up if you looked at this prior to the lecture, which by the way is the right way to go. Okay, some people were looking, all right. Let's design sheepdog game. Player is a sheepdog trying to herd sheep into a pen. So you would have a joystick or up and down, left, right, up, down arrow keys or something like that, ASDF. And as a player, you're moving that gray circle around and trying to herd the sheep into the pen. Think about what objects you would want for this game. Who can name an object that would be natural to this game?
The sheep.
The sheep. What else? We got sheep. We got to get the other one.
Dog.
Dog.
And the pen.
And the pen, or the terrain itself. Right, yep. Yep. So those are natural objects that come from this. There are other objects that you may not think of yet that we'll talk about, and one of them would be that this guy here, this circle representing the sheep. I'll introduce the seed of an idea, and I'll spend the rest of the semester convincing you it's true. That circle, that white circle is not a sheep. That white circle is a white circle. It's a representation of the sheep. So you actually have, to do the sheep, at least two objects. One is the sheep itself that keeps track of what the sheep is doing, and the other is the circle that tells the player who's playing the game where the sheep is. So one is the actual sheep object, and the other is just a representation of the sheep. And we'll want to tease those two things apart. We'll talk about that a lot more as the semester goes on. I used to do a short course in simulations for students when I was at UCF, and I would start out and put up a map of Florida, and I'd say, "What is this?" And they'd say, "It's Florida." And I would say, "No, it's a map of Florida." It's a representation of Florida. They are two different things. So a couple things about this picture before I move on. Number one, let's get in your brain that the thing you see on the screen is never the actual thing. The thing you see on the screen is just the representation of the actual thing. And number two, when you talk about graphics for your projects, think along these lines. Think stupid simple. Don't make life hard for yourself. You know, there's no way in one semester with one person you're going to create a fully developed reality physics-based three-dimensional dungeon crawler. All right, you're gonna want to go through this kind of simple graphics. And by the way, I've seen some really good games, really good games. Why could you not make the graphic representation and the object properties into one object? You technically could, and it would be the most messiest thing you could do, because the graphics objects come prepackaged and they have certain jobs, and you shouldn't tie behavior to those. And one of the reasons you wouldn't want to is think in terms of, if you know what a skin is in 3D modeling, where they make the shape of an object and then they put a skin over it. If you wanted to change that sheep representation from a circle to a square, or a picture of a sheep, or an animation of a sheep, you would have to redo the whole thing. But by keeping those two separate, the sheep and the representation from the sheep, you can just plug and play a representation of anything you like. So it's much, much better design. Once you'll see when we start to do graphics, trying to embed the behaviors into the graphics is really ugly, because graphics itself is fairly ugly. So keep those things separate. And that's a good question, right? Keep asking those questions. All right, so the objects that we've mentioned are sheep, dog, and then terrain. If you look at attributes for sheep and dog and start to think about, okay, I've got a sheep and I've got a dog, and you know, what do I need to keep track of? And I've listed some. You almost certainly would have more, but I've listed some. You would have X location, Y location for the sheep, X location, Y location for the dog, X speed, Y speed, max speed for the sheep and for the dog. The methods you might have that modify those attributes are movement methods: move, vocalize, speed up, slow down. You would have more. You could think of more. It depends on what you're doing with your game design at this point. But a couple things to look at. One is, look at how I'm naming these things. I'm saying X location, I'm not just saying X and Y. I'll reinforce that later and repeatedly throughout the course. Name your attributes so that people know what they do. And if that means you need a big long name, oh well, you need a big long name. Eclipse and other systems by which you do programming will help keep track of that for you. You'll autofill, so you don't worry about spending all day typing. Type a few letters and the autofill will work. So name them what they are. And then the second thing to notice is that these are virtually the same for sheep and dog. Terrain is wildly different. Notice under terrain I don't have any methods, because the terrain kind of just sits there in my vision of the game. It doesn't do anything. So if you want terrain that does stuff, you know, mountains suddenly pop up randomly, you would have methods for that. But for this, my terrain just sits there. Now I'm only showing methods that might actually change the attributes. It might be useful to be able to just get access to the attributes, to see what the attributes are, and you would include other methods for that, but they're not shown here. So if we look at these types of objects, sheep, dog, and terrain, those are the categories. We call them classes. So I have a sheep class, but look in my game. How many sheep do I actually have in this picture? 3, right? How many sheep classes do I need? Well, the sheep are identical. So they behave the same. They have the same attributes, even if they have different values for the attributes, like different locations. Even if they have the same attributes and methods. I only need one class. I only need one design. And from that one class or design, I can create 3 sheep objects. Think of your class as a design. Once you have a design, you can make as many copies of that as you want. Think about, some of you took EGR 120 and you had to design stuff, right? You had to draw stuff. Let's say you drew a bracket. You can't hang a door or you can't hang a shelf with a picture of a bracket. with a design of a bracket. You need an actual bracket. But before you have the bracket, you have the design of the bracket. And once you have the design of the bracket, you can make as many millions of brackets as you want. So you would have one sheep class, which is the design, and then you would create these sheep objects. And by the way, how do you do that? If you need a new sheep, you literally say in Java, new sheep, and you get a new one. Same with the dog. Even though there's only one, you would have a dog class, and then you would say new dog one time to get that one dog. So they're called classes. Now, the class is technically speaking not the object. It's technically speaking the design, while the object is called an instance of the class. It actually allocates memory from things for that specific object. They are technically different things. We almost always ignore that. Everybody talks about objects and classes as if they were the same thing, and that's pretty normal. And normally, 99% of the time, that's just fine. But please be aware of that distinction. And if I ever really need to know, wait a minute, are you talking about the class or the object? Then I'll ask you. In addition, just because you make a class, don't forget to make the object. One of the most common mistakes I see when students need help from me, they're saying, well, I tried to change this value and the computer crashes, the program crashes. And I'll look at it, oh yeah, and I know why. You built the class, but you never built the object. You designed the class, but you never actually built an object. So if I built a sheep class, but I never made new sheep, that dog would be running around chasing nothing because there's no sheep. Now, even though these methods are called the same thing, they would behave differently. For example, the dog movement method is based on user input, joystick input or up, down, left, right arrow key input, right? But that's how the dog moves. The dog moves based on responses from commands from the player. And how do sheep move? Well, they're going to move differently. They're, as simple would be they always just run away from the dog. So as soon as maybe outside of some radius, the sheep just stand still, but once the dog gets close enough to them, they run away. Those are different behaviors. So you would have different pieces of code inside the move method for the sheep and the move method for the dog. And similarly, I just put in vocalize just because it would be different. The sheep, blah, 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 and the dog, arf, 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 or woof, 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 those kinds of things. The name is the same, but the code that you write would be different. The result would be different. But the fact that they have the same attributes and names, at least in my simple model here, means that we can introduce a new efficiency. We can say, wait a minute, the sheep and the dog have the same attributes and they have the same move methods. How can I combine that? Maybe I could create a generic animal, and I'll call it animal, a generic animal. And then I can build the sheep and the dog from the animal. So the way that works is you would build animal, that's another class. And then when you build the dog class, you don't really build anything. You just say dog extends animal. This is called inheritance. The technical term is extension. I'll explain that in just a second. But you say dog extends animal. Now, when you say dog extends animal, what happens? What happens is the dog, for free, gets all the attributes and methods that the animal has. So that's why it's called inheritance. The dog inherits those things. The attributes are the same as an animal. The methods are the same as an animal. But we want the dog to behave like a dog, or actually we want it to behave like the dog does in the game. So what can you do? You can change the methods. You can write brand new code for those methods. And even though they have the same name, now it's going to behave differently. So I say, okay, I create the animal. Then I do dog extends animal, sheep extends animal. Now I've got dog and sheep, and I can write the methods where the dog barks and the sheep baas, where the dog moves based on player input and the sheep moves based on where the dog is. But I'm getting all the same method names with the correct behavior for the dog and the sheep. This is called inheritance, and it is a core part of the object-oriented paradigm. Now, what's this word extends? Why doesn't it say dog inherits animal, right? It says, no, it doesn't say that. It says dog extends animal. Why is that? Because not only does the dog get all the attributes that the animal gets, but if you wanted to, you could add new attributes for the dogs. In other words, the dog is an animal plus more stuff. It's an extension. So the dog could have more attributes if it needed to. The dog's methods, you could actually add, in addition to modifying the existing methods, you can add new methods. So it's an extension, and that's where the term comes from. Now, let me do one more slide and then we'll talk. Whoa, don't do that. This is a core principle in the object-oriented paradigm. It's borrowing from biology when we talk about inheritance. Generally, we call that generic class the parent. We call the more specific class the child. The one that's the extension is the child. The correct term is superclass and subclass, but nobody says that. They always say parent and child. You want to know superclass and subclass when you're in an interview. So you're going to get an interview for an internship or a job. Toss out the college word, right? Toss out superclass and subclass. The child inherits them all, modified as required, and can be added to, extension. Parents can have many children. So in this case, the animal is the parent, the dog is the child, the animal is the parent, the sheep is the child. So the parent can have multiple children. Each child can only have one parent, though, in Java. In some programming languages, you can have what's called multiple inheritance, so that the dog could have multiple parents. From a program semantic standpoint, from a program compilation and software understanding standpoint, single inheritance like this is much cleaner. So Java is cleaner. This is something that you're going to do for some of your homeworks and definitely for your project. The project requires that you have at least one example of a non-trivial inheritance. So you'll do this thing where you create a generic thing and then you'll create subclasses of that thing. Okay, so why do that? Why not say, I can do a dog and a sheep and all I have to do is cut and paste all the dog stuff into the sheep stuff? What's the advantage to this? It's a core principle of the object-oriented paradigm. It's actually a big advantage of the object-oriented paradigm, but why? What's the advantage here? Or advantages? Any thoughts? If you wanted to add another component, expand on that, Carly. And Evan says compress the amount of code. You're right, create more children. And Carly says a third object. Give me a third object, Carly. I'll do it for you. Groundhog. What if it was important to have groundhogs in the game for some reason? Well, you've already got the animal. You just extend it to groundhog. Evan says it compress the amount of code. You're right. Right. So that's another big reason. It's easier. It's less work. Good programmers are lazy. We do as little work as possible. I shouldn't include myself in good programmer category. They do as little work as possible. So number one, it's easier, less work. Number two, Carly brought it up. It allows for expansion. It allows you for later on adding things that you may not have thought about early on, or a new customer comes along, you have a new requirement. So it's easier. It's also less prone to error. If you do the cut and paste method, or you're going to copy over by retyping, today I type sheep, and then Friday I type up dog. I have to remember the names of all the attributes for the sheep and the dog and make sure they match. And I'm a human. What are humans really good at? We're good at making mistakes, right? We're good at screwing up. So by doing the inheritance, but since it happens automatically, you're not nearly as prone to error. And then the last thing is programs can run more flexibly and less likely to crash, and you don't have to create them for very specific things, because if I wrote my program that worked on animal, in other words, all of my software worked for animal, then it works for dog too, because a dog is an animal. And it works for sheep too, because a sheep is an animal. And if I needed to create groundhogs, which I hadn't even thought of until Carly brought it up, it would work for that too, because a groundhog is an animal. So it's really efficient, less error prone, and time saving for the programmers. You can have a subclass of a class and a subclass of a class and a subclass, right? You would actually have, Carly's asking about, would that be a separate program file? It would actually be, we put these in files and the extension is .java, and that's the class files is .java. You compile them because they become .class. But here, the way I have this set up right now, I would have 4 separate files. I would have animal.java, and then I would have dog.java, sheep.java, terrain.java, 4 separate files. And I would need additional files to show the graphics and all that good stuff to kick off the program and to manage the game, that kind of thing. Those aren't shown here. But what I've shown here, there's four separate files. You can include Greyhound extend, dogs, pug extend. Yes, exactly, Evan, you can do that. And we'll see examples of that. For example, when we do graphics, you'll see that there's long lines of ancestry for these things, 3, 6, 7 layers deep. And technically, every object you create is actually an extension automatically. You don't have to worry about it. Of this, there is a top-level class in Java called object. It's the most generic class, and so technically, everything you create is a child of the object class or a descendant of the object class. You tend not to have to know that until you're in, way up into doing some sophisticated Java work. Those are good questions. Any other questions before we continue? Okay, so the idea here was to get you used to the idea, first of all, okay, we're going to talk about objects in the class. What the heck are they? That's what they are. They're software pieces that do a specific job or jobs that are described, that have state described by attributes, and they have methods by which you can change the state. We'll also add in methods by which you can just query the state. You might need to know, hey, what's the X location of sheep number 1? And you should be able to ask that class, hey, give me the X coordinate. We'll talk about that again later in the semester. Just giving you the overview. Okay, so the benefits, it's easier. You get everything for free. You don't have to cut and paste or recode everything. You're not likely to make a mistake. It's less work. You have the same names for the same attributes everywhere, so it's easier to understand the code as well as to operate the code. And you can create new objects that you never even thought of later on. And if you design your code to work at the higher level, at the animal level, it doesn't matter what weird animals you create in the future, it will work. Here's a different example. This is actually the original example. This is the beginning of the object-oriented paradigm, which was in I think in the late 70s, early 80s. Some people were doing simulations of ships in harbor kind of thing. And they noted a few things like, gosh, all these ships are relatively self-contained things. Maybe we could program them that way. And all these ships share a lot of attributes. They all have tonnage and speed and turn radius and fuel levels and other things. And they have the same kinds of behaviors, but they differ in their behaviors. So maybe we can take advantage of that. And so they ended up actually creating a brand new language and a brand new paradigm as part of that project. That's like you saying, gosh, I have a math problem to solve. I'm just going to invent brand new math, which you are allowed to do, by the way. Newton did it, Leibniz did it, you can do it too. So the idea here is all these ships have very similarities in terms of their attributes, but they have some different behaviors, right? A container ship behaves differently than a passenger ship, which behaves differently than an aircraft carrier. And you can get radically different behaviors out of these things relatively cheaply in terms of software construction cost. You know, it's bad when ships run into each other. That's the job of a tugboat. Bad when ships go underwater. That's the job of a submarine. So you can have, through extension, unique behaviors. And yet, if you designed everything just to work with ship class, all those ships can play together. It all works out fine. And we're going to do this over and over and over in the course. I will introduce objects early on in the homework series, starting with the second homework, not where you have to create them, but just to get you used to seeing them and working with them. And even in the course examples that I'm starting with next week, I'm going to start with simple stuff where we work within the class, but we're going to basically do things in an imperative model, and then from there go into okay, what does this really look like? You know, you normally have an object, and then you have another object that works with it. So I'll give you examples of that early on. Okay, why would we do this? What was the whole point of the object-oriented paradigm? In addition to the software efficiencies that you get from this inheritance, there was probably the single major problem. Remember the history of programming languages, computers started showing up in the mid-40s, 1940s. And that was my dog, by the way, groaning, if you've heard that. And by the time we got to the 60s, when businesses were really starting to use these things and IBM was making a whole lot of money, the software was starting to get complicated. And the problem with the older models, the older paradigms, like the imperative paradigm, which says, hey, go top down, right? MATLAB is imperative. The way you use C++ and CS225 was probably imperative. It was effectively, okay, start at the top, start at main, do this line of code, do the next line of code, do the next line of code, right? Top down. That's the imperative model. The problem with the imperative model is that everybody has access to the same memory. And when you start to get large project teams, you know, I'm talking about 200, 300 people working on the same piece of software, they start to step on each other's memory. And you put some value in for X, and then you go to get it later and it's changed and you don't know why. It's because somebody accidentally stepped on your data. This was a big problem, and that's a tremendously difficult bug to find. So with objects, the attributes are contained within the object. And as a class designer or as an object designer, you get to say who has access to that data. You get to say how they access that data. You protect that data. And that's called data encapsulation. This is the single biggest successful part of the object-oriented paradigm. This works. Huge success here. Very good. I'll talk in a little bit about when you're creating attributes that you can specify who gets to see them, and the correct answer is nobody ever gets to see them. Right? My object is the only one that can see these things directly. So that's the big one. The other was code reuse. So we talked a little bit about that before. I can do animal, and then it's much easier to create the sheep and the dog by extending animal. There was a false hope that people could just make big libraries of objects and then say, okay, here's how I'm going to write my software. I need object number 28 and 62 and 49 and 28, and I'm going to stitch those together, and that's my code. And that never happened. That never happened. It's too complex. There are people still trying to do that. There's a whole paradigm out there called component-based software design, component-based software design. And they try to do exactly that. It has not been successful, and it has been formally proven to be chaotic in the mathematical sense. So from a security standpoint, people are pretty leery of it. Now, we all know that you do get some benefit from existing software. I think a lot of you that do coding on your own as a hobby, you've probably imported libraries before, you've imported APIs before, and the same is true for Java. There are Java libraries out there that you may import and use for your projects. When I have people that want to work with Excel, you know, Java to Excel. They bring in an additional library that's already been written for them. That kind of thing works. But that's no more code reuse than you get out of any other paradigm. And then the last was understanding. People were hoping for software understanding. The bigger software got, the more complex it got, the harder it was to understand. Software understanding is an intrinsically difficult problem of software engineering. In other engineering forms where you're creating physical things, you can build the part and hold it in your hand. You want to see if two things fit together, you build both of them and put them together. They either fit or they don't, and if they don't, you know how to fix it. You can't do that with software. It's hard. Software understanding is difficult. So nobody knew what the heck was going on with the code, and everybody was hoping with software that, with object-oriented software, that since everything was broken down into objects, it would be conceptually clearer what the software was doing, and that turned out just not to be true. Other attempts had been made prior, component-based software, block software, that kind of stuff. The approaches are typically the same. You take the big problem and you chunk it down into smaller problems that are each understandable, and then you put those together. And the same thing with object-oriented. You take a big problem, a big job you want to do, you break it down into smaller jobs, you make objects out of those smaller jobs, and then you should be able to understand the software. And it just turns out, no, still not true, still difficult. So of these three things, these are the three main drivers. Data encapsulation is successful, code reuse somewhat successful due to the notion of inheritance, software understanding. Nobody knows what's going on in software. And that's not a criticism of people, that's the state of the nature of the problem. I don't know, maybe you guys have had that experience too. This works, but I don't know why. Doesn't work, I don't know why. Oh, that's my dog. And we've all heard of the people that are, there's a comment in the code somewhere that says, we don't know what this code does, but when we take it out, it doesn't work. So leave it alone in production code. Let me see your dog. Yeah, someday. She's running around the house right now because she heard a noise. Yeah, we can rotate them. We've got my wife and I have 3 of them. So. Okay. I've only got 3 minutes, so let me see. Let me get through this really quickly. So Java notation to find out what you're going to be looking at. Conventions, the class names, capital A starts with a capital letter. Animal, sheep, dog, terrain, they all start with a capital letter. So you know right away when you see something that starts with a capital letter, it is in a class. Attribute names and variables, lowercase. They start with lowercase, and make them long, make them descriptive. Tell people what they're doing. It's okay. And that means you're going to have multiple words or phrases in there. It starts with lowercase, and then every time you begin a new word or phrase, it's a capital letter. That's called camel hump notation because it looks like camel humps. Variables that are created local to a method. That's when the distinction between attribute and variables, by the way, which we'll discuss more. Attributes belong to the class. Variables are only inside of a local method, named the same way as attributes. Constants, all caps. Those are conventions. If you don't follow those conventions, will your code compile and run? Absolutely. Will you get a job? Maybe not. You're not showing people that you know the community, right? The culture. In addition, you can say that everything that you create, you get to decide who gets to see it. So you can put a modifier up there, private, public, protected, which is rarely used. Public means everybody can see it. Private means nobody can see it. The rule is basically set all your attributes private. Make your data private. That's data encapsulation. Make many of your methods will be public. And by many, I mean 95%. Your classes will be public. There's no point in making a class that nobody can touch. So classes are public, data attributes are private, methods tend to be public. And the reason that you do that is, let's say we need to know where that dog is, or that sheep is, right? If you need to know where that sheep is and we've made the X and Y locations private, nobody knows where it is. Well, what do? You create a public method where you ask the sheep, hey, where are you? Give me your X coordinate, give me your Y coordinate. And that way external entities have access to the data, but it's controlled access. The designer of the class controlled it. We can even allow external entities to set those attributes. Hey, put the sheep here, put the sheep there. but we're doing it in a controlled fashion. So if somebody tries to put your sheep out of the game, you don't accept it, you reject that. So keep the attributes private, and then you use public methods to allow other objects to interact. Lastly, we have to declare everything. What do I mean by declaration? In MATLAB, I think you could just use variable names and just start using them, and MATLAB was happy as a duck with that. Most programming languages don't like that. Most programming languages require that before you do something, before you use variable X, you first have to tell the computer that there is going to be a variable X, and that's called declaration. And languages that require declarations typically require at least two things, the two things being the name and the type. What kind of data are you telling me I need to deal with? So we have basic types: integer, which is a numeric integer value, it's int; double, non-numeric integer, numeric non-integer values; char, single character; string, sequence of characters. So you're going to see things when you look at the code like public class animal. What is that saying? Well, its name is animal. It is a class, and public, everybody can see it. But inside of public class animal, we might have private int xspeed. So the attribute declaration is private, nobody can see it, and it's an integer value, and its name is xspeed. Integer values for speed are probably not good. You probably want non-integer numeric values, so we would use double. So you could say public double xspeed. What's wrong with this picture? It's public. Don't make your attributes public. If you need max speed to be fixed, can't change it, make it all caps, and you can actually set the value right there. You can do that with any of these, by the way. If you're declaring a method instead of an attribute, I know I'm 2 minutes over, but I'll be done in a minute. If you're declaring a method instead of attribute, same trick, public or private. And then its name, followed by parentheses. That's the input parameter list. Right now I'm saying the move method doesn't need any inputs. It just will work. And then curly brackets. And what the code is, the code for the move method would go inside the curly bracket. So everybody can see it. Its name is move. It doesn't need any input, and I'm going to fill in these brackets later. Well, what's this int doing here? Well, if the move method returned a value, you have to claim what kind of value it's going to return, and therefore, if move value returned an integer value, you have to say that right up front in the definition. This thing returns an integer value. Now the problem, and you probably know this from functions, not all functions would return a value. Not all methods that you create will return a value. Maybe they're just going to change the attribute values but not return a value. How do you tell people that? You use this, void. So that's the way to say, I don't give you back anything. I might do some stuff, I might modify attributes, but I don't return a value. Okay. And I am done with these slides. I'm over time, so I would ask that you do questions by giving me questions on Canvas. And thank you for being here. We will see you on Friday.